In the last video, we looked at limit law 1. I am not at all concerned that you have the numbers memorized, but limit law 1 for finite limits, which said if you're adding two functions and then taking the limit, it's perfectly acceptable to take the limits first and add the results, provided each limit is a finite number so that you're getting a legitimate arithmetic problem. Rules 2 through 5 just say that for the rest of our arithmetic. Now, it may seem a little bit strange that there are 5 limit laws that deal with arithmetic because we only have 4 arithmetic operations. We've got addition, subtraction, multiplication, and division. The reason we have 5 rules is that both rules 3 and 4 deal with multiplication. One is just sort of a special case of the other. All right, so Rule 1, and again, the numbering isn't important. Rule 1 is the sum rule for limits, or the sum law of limits. Rule 2 is the same thing, but for subtraction. If I'm subtracting two functions and then taking the limit, I can take the limit of each piece and then subtract, provided I'm getting a legitimate arithmetic problem, so both limits do need to be finite numbers. Rule 3 is one of our multiplication rules. Rule 3 is where we deal with this constant c. So it deals with a multiplication problem where one of the factors is a constant, just a single number, and another factor is a function that might vary with the input. And it basically says you can just factor out that constant. So you can multiply f by the constant and then take the limit, or you can take the limit and then multiply by the constant. Again, this only applies for finite limits. Rule 4 is the more general multiplication rule. If you're multiplying two functions together and then taking the limit, you can take the limit of each piece and then multiply the results, again, assuming you get a legitimate multiplication problem, which is only allowed to involve finite numbers. Okay. So 3 is just a special case of that. 3 would be the case that one of these factors is a constant, and the limit of a constant is just that constant. Okay. And then 5 is our division rule. So if I'm dividing two functions and then taking the limit, I can take the limit of each piece and then divide. That, of course, requires that I have finite numbers, and with division, there's one additional rule, and that's that the number that we get on bottom, so the limit of the function that appears on the bottom, can't be 0, because we know we're not allowed to divide by 0. Okay. So basically, all of these rules say, if you're doing some combination of arithmetic and taking limits, you can do the arithmetic first and then take the limit, or you can take the limit of each piece first and then do the arithmetic. Again, assuming that you get a legitimate arithmetic problem, so that you're just dealing with finite numbers and you're never dividing by 0. Okay, excellent. I want to just get a little bit of practice applying these limit laws. So I've given us the graphs of two functions, f of x and g of x, and I've written down two limits here that I'd like to try to evaluate. So I'm going to suggest we're going to evaluate these by using the graph. So I need to tell you that each tick mark represents one unit, and points or holes that appear to have integer coordinates do. With that information, go ahead and pause the video and see if you can evaluate these two limits. All right, welcome back. So I've written out the answers to these problems here. Notice here I was multiplying two functions and then taking the limit. I said I can take each limit first and multiply the results. Over here, as we're approaching -1, looks like our y values are approaching the y value of this whole, which would be -2. So this first limit was -2. And on the graph of g, at -1, we're approaching this whole that has a y value of 2. -2 times 2 is -4. Now here, I wrote out that I was going to take each limit individually. It's totally legal to do that here because this limit law applies. It's perfectly legal, though, to also just say, hey, that's going to -2 and that's going to 2. I don't need to use that arrow notation because I can write the separate limits but that takes a little bit less time to write. So sometimes that arrow notation is just a convenient shorthand as I'm working things out. With this second one, we were subtracting two functions. And so I said, well, we can take the limit of each one and then subtract. As x approaches -2, that would be here. There's actually a point there. Looks like at -2, 0. So f is approaching 0. The limit as g approaches -2, that's going to be the y value of the whole there. Looks like that's up at, that's up at 3. I'd written 2. That's actually up at a height of 3. So that would be 0 minus 3, which is -3. Okay, excellent. Let's just take a look at some interesting things where stuff could go wrong. Let's suppose I wanted to take a look at the limit as x goes to -2 of g of x over f of x. Okay. Now, if I naively think that I could apply the limit law, and I write the limit as x approaches -2 of g of x over the limit as x approaches -2 of f of x, nothing wrong with my thought process here. That's usually what I would do when I have something like this. But then we just evaluated and saw that this was 3 and this was 0. Oh, I'm like shaking. That's horrible. Let's get rid of that. That's awful. We cannot write that, which means we also can't write that. Okay, that's writing 0 on the bottom, because what I've written on the bottom is equal to 0. If the limit law doesn't apply, you cannot use it. Okay, so there may be times when you don't notice that the limit law doesn't apply until you've written something like this. That's fine. I have no problem with you starting down a certain path and then saying, oh, this is a dead end. Turn back, acknowledge that that is not a path that will work, and cross that off. Do not write mathematical atrocities. Dividing by 0 is a mathematical atrocity. Do not write that on any work that you're submitting for me to grade. Here, I could use my arrow notation. So I could say that's going to 0 and that's going to 3. So I've got a situation where the bottom is going to 0 and the top is going to 3. I would do my sign check here. So, whoops. If I look at the top, if it's close to 3, it's going to be positive. Now over here, if we're close to 2, is the graph positive or negative? Well, I can see that to the left of -2, the graph is positive because it's above the x-axis. To the right of -2, the graph is negative because it's below the x-axis. So I've got an indeterminate sign, and so that does not exist. Okay. Don't get that, though, just from the fact that the denominator is 0, because let's now change it. Let's look at this as the limit as x approaches -2 from the right of g of x over f of x. Now still, the bottom's going to 0 and the top is going to 3. When I do my sign check, the top is still positive, but now we're approaching -2 from the right. So I'm just looking at this part of the graph right here. It's below the x-axis, it's negative. So when I do my sign check, I get a positive divided by a negative. That's going to give me something negative, and so that one-sided limit would be -infinity. Okay. So the limit law didn't apply here. I needed to recognize that, but I still had some other tools for evaluating the limit. Let's just deal with what happens at 1, because I can see I've got an infinite limit then on the graph of f of x. So let's just look at the limit as x approaches 1 of f of x plus g of x. Okay. Now, having seen that there's an infinite limit here, I'm not even going to try to apply a limit law. I'm just going to use my arrow notation. So that's going to infinity. G looks like it levels out at a height of 1, so g is going to 1. So I have one term that's really, really big and positive, and I'm going to add 1 to that. I think it's still going to be big and positive. Now, I can't literally take infinity and add 1 to it, but I can say if I've got something that's big and positive, adding or subtracting, for that matter, any finite number isn't going to change the fact that it's big and positive. Now, sometimes when people see this, they really want to write infinity plus 1. They know they can't literally write that, but they just want to as informal work to help them in their thought process. It is not okay for you to write that this equals infinity plus 1. If you're going to write that as informal work just for yourself that you don't want me to grade, you need to clearly indicate that that's what it is. There are 2 ways to do that. 1, you can write me a note. Dear Carla, I understand that infinity is not a real number. I understand that arithmetic is only defined for real numbers. Therefore, I recognize that infinity plus 1 is nonsense. I do not mean it literally. Please do not take off points. Sincerely, with much respect and admiration, and then sign your name. Now, on a timed exam, it might take you a while to write that note, but you still might want to be able to write this just for your own sake, to be able to look at that off to the side, not set equal to anything, to try and figure things out. This is my shorthand for doing that. You know how when you put something in quotes, it means you don't mean it literally? That's my shorthand for I don't mean this literally. Okay. Now, that's a notation that I sort of developed. It is not universally understood in the mathematical world. So, when you move on to Math 3B, if you put something like that in quotes, your teacher may or may not know what you're talking about. So recognize that that's an informal convention that I will allow you to use this semester. As you move on and have other teachers, now some of you might have 3B with me at some point, that would be wonderful. But as you move on, if you have other teachers, make sure you check with them about how they would like you to notate things, and whether they're okay with you having informal stuff that you don't want them to grade because you know it doesn't actually make mathematical sense. Okay.